Welcome to Study Loop.
So in this problem, we are given a common water that contains 75 ppm calcium carbonate and 55 ppm magnesium carbonate. So we have to calculate the mass of sodium carbonate that is required to remove 90% of these ions from 10-liter water. So to do that, first we have to find out the ppm concentrations of calcium carbonate and magnesium carbonate in terms of number of moles. So to do that, so number of moles of calcium carbonate is, we have 75 ppm, that means 75 milligram per 1 kg, and then we convert the milligram to gram by multiplying it by 10 to the power minus 3 gram 1 milligram, and then we'll convert the kg to liter. Since it's 1 kg means 1 liter, and we have to find it in 10-liter. So this will be 10-liter, and we have to divide this. Since we are trying to find out the number of moles, we have to divide the mass by the molar mass, which is 100.08 gram per mole. And the result will give us 0.0075 mole calcium carbonate in 75 ppm calcium carbonate. In same way, we can find the number of moles of magnesium carbonate, and if we just follow the same rule, we have here 55 ppm magnesium carbonate. If we just convert that to mole, and just to make sure that you have to do all these things, and just in case of the molar mass, the molar mass of magnesium carbonate is 84.31 gram per mole. So this just applying the same process, you will find the number of moles of magnesium carbonate as 0.0065 mole magnesium carbonate. And now we have to calculate, so the total mass here will be, and the total moles here will be is the sum of that two moles, 0.0075 plus 0.0065, and the sum will be 0.014 mole. And what we have to do here, we have to remove 90% of this number of moles. That means in the solution we will have 10% remaining. So the number of moles of the ions remaining in the solution is 10% of this. That means 10 by 100, and we will get 0.0014 mole. So this much ion will be remaining in the solution after we adding sodium carbonate to remove them. And so again we have to find out how many of these moles are calcium carbonate, and how many of them are magnesium carbonate. So if we look at the Ksp value of calcium carbonate and magnesium carbonate, we will see that the Ksp value of calcium carbonate, if we just write down here, Ksp value of calcium carbonate is 4.96 times 10 to the power minus 9, and Ksp value of magnesium carbonate is 6.82 times 10 to the power minus 6. So from here we can see that the Ksp value of calcium carbonate is very low if we compare it to the Ksp value of magnesium carbonate, and that means with the addition of sodium carbonate all of the calcium carbonate will be precipitated. As we know that um, the compound with lower Ksp value will be removed or will be precipitated first. That means um, after the after the addition of sodium carbonate, what we have here will be totally magnesium carbonate. So we don't have any calcium carbonate left here, as it's having a small or lower Ksp value. All of its ion will be removed already. So now we have to set up the Ksp value expression for magnesium carbonate. So magnesium carbonate will be dissociated as Mg2 plus CO3 2 minus. So that means the Ksp expression for this will be simply the product of these two ion concentration. That means Mg2 plus times CO3 2 minus. And from here we'll have to find the CO3 2 minus, the concentration of CO3 2 minus. Here we'll be able to find the mass of the sodium carbonate we require to do this. So the Ksp value for magnesium carbonate, we have just seen that it is 6.82 times 10 to the power minus 6. And the magnesium ion concentration is basically this number of moles over, so here since you're dealing with 10-liter solution, if we just divide this number of moles of um, basically the number of moles of magnesium carbonate, 0.0014 mole over 10-liter, that means we will have 0.00014 mole per liter or molar. So this is basically the concentration of magnesium carbonate. But since from 1 mole magnesium carbonate we will get 1 mole magnesium ion, that means this concentration is also the concentration of the magnesium ion. So you just put this value here, 0.00014 times the concentration of our carbonate ion. So if we just solve this, we'll find the concentration of the carbonate ion as 0.0486 mole. So this is the concentration of the carbonate ion. Now this is the concentration of carbonate ion, means this is also the concentration of the sodium carbonate. Since from 1 mole sodium carbonate we'll have 1 mole carbonate ion, that means this is also the concentration of the sodium carbonate. Now if we try to find the number of moles of sodium carbonate, we will have mole per, that means 0.0486 mole per liter, and if we just multiply it by the volume, which is 10 liter, we'll get the number of moles of the carbonate. And so the result here will give us the number of moles of the carbonate. And if we just divide this by the molar mass of sodium carbonate, which is 105.99 gram, this is the molar mass of sodium carbonate, then we'll find the mass of sodium carbonate, which is 51.6 gram. So here we have Na2CO3. So yeah, so that's how we are actually finding the mass of sodium carbonate required. So once again, so what we have done here is we have found the concentration of the carbonate ion from the Ksp expression of magnesium carbonate using this. And here, since the carbonate ion is also coming from the sodium carbonate we are adding, that means the and we can get 1 mole of carbonate ion from each mole of sodium carbonate. That means the concentration of sodium carbonate is basically the concentration of the that means the concentration of the carbonate ion is basically the concentration of sodium carbonate. So, and then if we just multiply this by the volume of the solution, we will get the number of moles of the sodium carbonate. And then if we just divide that by the molar mass of sodium carbonate, we will get the mass of sodium carbonate that we need to add in the solution of a 10-liter water to remove 90% of the calcium and magnesium ions.